Welcome to Hartman Math. Before we get to counting principles, let's take a look and review early Chapter 9 sequences and series with our warm-up. Pause here as you work through the three problems. Play when you're ready. All right, so number one, if we can kind of recognize what's going on, we seem to be multiplying each time by -3, so it is geometric. So the 18th term would be the first term times the common ratio to the power of 1 less than the position. So 17th power, pretty big number there. There we go. Number two, evaluating a sum. It is a partial sum, and this is exponential, so it is geometric. So we're going to do S sub 8 is equal to A sub 1. So substituting in a 1, we're going to get 100 times 1 minus 0.3 to the 8th divided by 1 minus 0.3. And lastly, evaluate infinite sum. Only way we can do it is if it's geometric. So explore, does it have a common ratio? Is the fourth term divided by the third term the same as the third divided by the second? Same as the 8 divided by 10? I think it is. And 0.8 for a common ratio does qualify for infinite geometric sum. So 10 divided by the 1 minus the common ratio of 0.8, and we get a sum of 50. And this is lesson 9.6, counting principles. So we're going to start with selecting pairs of numbers at random. Where you have 6 cards, and on the cards are the numbers 1 to 6. They're placed in a box. We reach into the box, pull a card at random, write down its value, put the number back in the box. How many ways can two numbers be drawn and have a sum of 10? So let's think about the first card that we pull out. Could it be a 2? Well, if it's a 2, then the next one's going to have to be an 8. There are no 8. So the first card cannot be a 2. But the first card could be a 4. In which case the second card would be what? It'd have to be a 6. We could draw the first card being a 5. In which case that requires, since we're throwing it back in, we could get the 5, same card again. We could get a 6 on the first card and a 4 on the second card. So there's going to be 3 possible ways that this can happen. Let's take a look at the same idea, this time but without replacement. So when we take the card, we do not put it in a back in the box. We just kind of set it aside. So again, if we're going to come up with the sum of two numbers, again, the first number can't be a 1 if we're going to have a sum of 10. Because there's no card of 9 in the box. But we could get a 4 and a 6. We cannot get a 5 and a 5, because once we pull the 5 out and set it aside and reach back in, there is no other 5 in there. So we can't have that happen. But we could get a 6 and a 4. So there's 2 ways. So the fundamental counting principle is if we have 2 events, and this can be extended to more than 2 events, but we have 2 events, and we've got the first event can occur in M1 number of ways, and the event 2 can occur in M2 different ways. The number of ways that the 2 events can occur, the first event and the second event, and the key word there is we would multiply those together. And as I said, this can be extended to 4 different events, which would be M1 times M2 times M3 times M4. So let's see about using that fundamental counting principle. Let's say you have a password for your account at matrices.com, and your password has to be a letter followed by a digit. It is not case sensitive. How many different passwords are there? Well, there's 2 events. There's character number 1 and there's character number 2. First character has to be a letter. How many choices do we have? Once again, it is not case sensitive. So there's no difference between a capital A and a lowercase a. So there's 26 letters. What if it was case sensitive? Then what do we have here? Then it would be 52. 26 capitals, 26 lowercase. We're just going 26. And then it's followed by a digit. How many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. 10 digits. So those are our two events. We multiply the number of ways each can happen. And that means that there are 260 passwords. Must not be a very popular website. Example number 5, now we're going to look at permutations. And what that means, there are 3 finalists in a competition for gold, silver, and bronze medal. How many ways can the medals be awarded? So a permutation is when we're looking at a group of things, or people, or cartoon characters, and we're choosing an order, and order matters. We're choosing how many get a gold medal, a silver, or whatever. In this case, we're choosing places. So order definitely matters, because you definitely want to be gold medal as opposed to bronze. When order matters, I'm really thinking in terms of a permutation. So if we look at this, just in general, we're going to award a gold medal. How many choices do we have among our contestants to award the gold medal? There's 3 of them. So there's 3 choices. Once the gold medal has been awarded, let's say to Phineas, then how many choices do we have for second place, the silver medal? Now there's 2 choices left. Then there's a bronze medal. Well, there's only 1 contestant left. That 1 contestant, there's 1 way of awarding the bronze medal. 3 events, multiply them together. 6 different ways that our medals can be awarded. So a permutation of n elements is the number of ways that can happen. N times n minus 1 times n minus 2 times n minus 3 and so on until we get down to 4 times 3 times 2 times 1. And if we remember from a previous lesson, that just means n factorial. So in our previous example, there's 3 of them and all of them get prizes and they are ordered. That would be 3 factorial. 3 factorial is 6. Permutations, order matters. So this time we have 5 finalists. Again, we're going to go and award an Olympic medal, gold, silver, bronze. So how many choices do we have for our gold medal? 5 choices, could be anyone. Eliminate that contestant, that cartoon character. How many choices do we have left for the silver? We got 4. How about for the bronze? 3. 5 times 4 times 3. So that 60 ways is the same as 5p3. Of the 5 contestants, 3 of them were chosen for a medal. So we didn't choose all of them like in the previous example. So we can type that under the calculator. So just like we did when we're doing combinations in the binomial theorem, you would type in 5, find the NPR button, which is in the graphing calculator, choose math, go to PRB, then you want to choose the one that says NPR. And then type in a 3 after that, and it's going to tell you 60. So permutations, if we're not choosing all of them, so in that last example, we didn't choose all of them. We chose 3 of the 5 to get medals. So if we're taking from the n elements and taking r of them, r at a time, then this is the way you want to look at it. NPR, our last one, so we're going to see in a second, 5p3. Of the 5 that we had to choose from, 3 of them get chosen for medals. 5p3. This is how it's calculated, but you don't really need to know that, as we're going to focus in on the NPR part, because that's how we're going to do it in the calculator. Now, in terms of distinguishable permutations, this is when we have looking at a group of objects and maybe there are some copies within there, some of the elements that are identical. So the way that we do the distinguishable permutations is the number of items that we're choosing from divided by how many copies are there of one of them, factorial, times how many copies of another, and so on. So in example number 7, distinguishable permutations, and ordering letters is a good way of kind of representing our situation here. How many distinguishable ways can we arrange the letters here? Now, it doesn't mean that when we rearrange them it's a different word, it's a different combination of letters. But our issue is if they were all different, then switching anything creates something different. But in this case, if I switch these two E's, it's not any different. So that's where this distinguishable permutations comes in. All right, so how many letters do we have? We've got 9 letters. That's going to go on top. Divide by. How many T's do we have? 1. So divide by 1 factorial. Now, if we don't put that, not a big deal, because 1 factorial is just 1. Dividing by 1 is not going to change anything. How many E's do we have? We have 4. So 4 factorial. How many N's? 2. 2 factorial. How many S's? 2. 2 factorial. So that's the way we're going to set it up. We're going to divide it. We might, depending on your calculator, might need parentheses there. We're going to get 3,780 different ways of rearranging the letters so that we get something that's actually distinguishable, that's different. Combinations, again, we looked at combinations back in the binomial theorem. Combinations NCR, this is how it's calculated. Don't really need to know that. You can just go find the NCR button, which we've already practiced before, in the calculator. When we're talking about combinations, order does not matter. It doesn't matter if you're chosen first or second. You just need to be chosen. For example, our Cartoon College freshman class is electing 2 class senators from this group. These are the 5 that are running. And how many ways can the 2 senators be chosen? Well, it doesn't matter if you're senator number 1 or senator number 2. So order does not matter. That's what makes this a combination. From our 5, we're going to choose 2 as a combination. 5C2. Let's go ahead and type that in. 5, and then press Math. Go to Probability, PRB, choose NCR. Hit that, type in 2 equals. We're going to see there's 10 different ways that this can happen. The exact same problem is if these people are all required to shake each other's hand once each. How many handshakes happen? 10. Because among the 5, handshakes are taking place between any 2 people. Example number 9, counting card hands. So when we're looking at combinations especially, looking at playing cards is a good way of representing that. So if you're not really familiar with a standard deck of 52 playing cards, you'll see this representation in your book where we have our 13 different kinds or ranks of cards, and we've got our 4 different suits of cards. So in the game, Texas Hold'em, you get dealt 2 cards. How many different hands could you be dealt? Well, does it matter the order in which you receive your cards? It doesn't, because when you get your cards, usually in a card game, you kind of rearrange them anyways. So if order mattered, you couldn't rearrange them. So order does not matter. It's a combination situation. All right, so how many cards do we have to choose from? There are 52. How many do we actually get? 2. 52C2. means there's 1,326 different starting hands of 2 cards. Continuing that, if you get dealt 3 cards, how many different ways are there to get 2 cards in one suit and 1 card in another? Separately, a separate problem, about 3 cards all in the same suit. All right, so let's look at this. We need to get 2 cards in the same suit. First thing that needs to happen is we need to figure out what suit it's going to be. Is it hearts, clubs, spades, diamonds? So how many ways are there to choose that? 4 ways, because there's 4 suits. So 4 ways of choosing the first suit. Now, within that suit, let's say, and specify and think of it, let's say we're talking about diamonds. We need to get from our diamonds 2 cards that are in the same suit. So, how many cards do we have to choose from? Well, there's 13 diamonds. Of those 13 diamonds, how many are we getting? 2 cards in the same suit. So we've got that taken care of. Now we need to get our second suit. How many choices do we have for our second suit? Because we have to get 1 card that's in another. Say it's clubs. So there's 3 choices left. If diamonds are out, there's 3 choices left. Now we need to get the last card. How many choices do we have for that? Since we're only choosing 1 card this time, because we've got 1 card in another suit, we probably don't need to do combinations. We could, it'll work out the same. We probably don't need to. But in those clubs, we could get any of those 13 cards. So we're talking about 4 times 13C2 times 3 times 13. You can do that on a calculator. Run that through. Should be 12, 168. What about our second situation? Probably actually a little bit easier this time. 3 cards in the same suit. So once again, since we're only getting 1 suit, so it's just the suit. We already know what that is. Got 4 choices. And again, let's be specific. What suit? Maybe hearts. Times, now we got to get the cards. 3 cards all in hearts. So how many cards do we have to choose from? In hearts. 13. Order doesn't matter, so combination. How many are we choosing? 3. We got all of our cards now. So if we do that calculation, we get 1,144. Example number 10, you're forming a 10-person committee. 9 women and 12 men applied. The committee has to consist of 5 women and 5 men. How many different ways are there to form that committee? You got to choose the women. Of the 9 women, you're going to choose 5 of them. And if you're one of those women being considered, it doesn't matter if you get chosen for the 3rd spot or the 4th spot or whatever. So order doesn't matter. And we got to do the men. And again, it's multiplying all these together. 99,792 different committees. That's it for today. See you next time.